Okay, hello to everybody online. Let me see how. 15 online, that includes us.
Oh, yeah.
So 10 plus our speaker online, and 1, 2, 3, 4, 5, 6, 7, about 8 in the room. So welcome everybody. My name's Mike Morrow. I'm the president of the St. John Center of the Royal Astronomical Society of Canada, and I'd like to welcome everybody. I'm going to start with an acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of the Beothuk, and the island of Newfoundland as the ancestral homelands of the Mi'kmaq and Beothuk. We would also like to recognize the Inuit of Nunatsiavut and Nunatuavut, and the Innu of Nitassinan and their ancestors as the original people of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. So thank you everybody for coming and for joining us online. We have an exciting talk tonight, but first I'm going to make some very short announcements. The first is that our meeting next month, February 19th, is going to be a members meeting, and we really need you, the members, to come up with a few things to present. So anything that's astronomy related, even if it's kind of peripheral, but some kind of project, something that you're interested in, something you've learned about. You don't have to be an expert in it. You develop your expertise we all develop our expertise by actually trying to explain things. So if there's something you're interested in, we want to get 3 or 4 15-minute, 10 to 15-minute presentations, show and tell, anything. So think about that, and please let us know, let myself or Randy know as soon as possible if you've got something you'd like to talk about, so we can start putting together an agenda for the next meeting. And the other thing I just wanted to raise, we've noticed when Randy does the membership, goes over the membership each month, there are we notice that there are some renewals where there's a couple of attempts first, and it says, what's the wording they use, Randy? Failed renewal, and then it works. And we don't quite understand what that is. So if you've had that situation, could you just get in touch with one of us and tell us what happened and what resolved it, or if it was just a mystery? And if you are having trouble with renewal, please persist or let us know. And maybe we can try and understand that and avoid that going forward. Okay. So, and I want to remind people that we have the Astro imaging contest again. It's open now, and the submission deadline is March 31st. We're looking for images that have been captured since January 1st, 2024. Solar system, deep sky, landscape, sketching are the categories. And you submit your photos to photos@stjohnsrsc.ca and use the subject line 2025 Astro Imaging Contest, so that we know that that's what they're there for. 3 images, maximum of 3 images per category per person. And we want this information. You can, this I think is posted on the website now, right? So you can go in and have a look at that. It's pretty basic stuff. The image size limit is 20 megabytes. If you send something that's exactly 20 megabytes and it bounces, you might want to try shrinking it a little bit. And we'll do the judging the same way we did last time, with an online poll, and the awards will be presented at our last meeting. And there may be some Jim Johnson has been collecting up some prizes from sponsors. So there may be more than just plaques. So that's some motivation. And for any visitors, I'll just remind you that the meetings are open to visitors, but there are some benefits to joining. One is our chat group, RSCNL Talk, which is a good forum for mentorship and sharing observations and alerts. There are some publications. And in the summer, sometimes we have observing sessions out of Butterpot, and we have low-cost equipment rentals. And there's a monthly bulletin that all members should get, and anyone, don't have to be a member, can sign up for the RASC weekly newsletter. And with that, I'm very pleased to introduce our speaker for tonight. He's Youseef Zaazou, and he's joining us very graciously from Alexandria, Egypt. So it's some awful time of night there. And he's going to talk to us about the topic of his master's thesis, which was AI to fill the gaps in astronomy. And Youseef got his BSc in applied math and physics in 2021 from Memorial, and he completed his master's in scientific computing, also from Memorial, just last fall with Terence Trico, and his thesis was mapping galaxy images across ultraviolet, visible, and infrared bands using generative deep learning. So I'm going to ask everybody at home to mute themselves and turn off their camera to reduce the bandwidth, since the bits are having to jump all the way across the Atlantic. And what I'm going to do now is I'm going to stop sharing. I'm going to ask Youseef to share, and then I'm going to have to slide his screen over so that the people in the room can see it. And hopefully, if there's any problems or any questions, send something in the chat, and Randy will alert me. And but hopefully everything will work fine. So I'm going to stop sharing now, Youseef, and you can unmute yourself and share.
All right.
And I'm going to slide you over here, and I'm going to mute myself. How do I do that? There we are. And so now.
Okay, I'm guessing you are muted, Professor. Can you all hear me? Maybe a quick thumbs up, Professor? Good. All right. Okay, good. All right. So my name is Youseef Zaazou. Hello. I guess following that gracious introduction, I don't have to waste too much time with this intro screen. So, all right, what do I? Nope. There we go. All right. So the outline of this talk will be we'll begin with what galaxies are and why studying them is important. Then we'll get into how they are studied, and we'll outline a bit the electromagnetic spectrum. Then we'll give a brief discussion of how generative AI can help. And then we'll go into the different types of models that I have been developing for the last year or so. And then finally, your results, discussion, and future work, and of course, questions if you have any. So starting with, what is a galaxy? Well, a galaxy for our purposes is a collection of stars. There's dark matter and other stuff as well. But again, for our purposes, we can think of them as a collection of stars bound together by the force of gravity. In the center is a supermassive black hole, which is somewhat irrelevant, but again, that's the gravitational center of any given galaxy, is this supermassive black hole. So why study them? Well, first of all, they allow us to track the existence of dark matter and dark energy. So dark energy is this mysterious force that is hypothesized to be behind the expansion of the universe. Dark matter is the mysterious substance that is hypothesized to keep galaxies together. So by studying and tracking galaxies, we can track these dark energy and dark matter, and it can also help us refine our understanding of cosmic evolution. And we do that by studying different populations of galaxies, because the farther out we look, the further back in time we are appearing. And so by studying closer versus far away galaxies, we can get an understanding or a better understanding of cosmic evolution. And I'll give you a second here to take in, some of you might already know, this is the Hubble Ultra Deep Field image. The original image, by the way, you can download it from the Hubble website. It's around 110 megabytes, which is quite large. And the reason is there's roughly 10,000 galaxies in this image alone. And you can see like some of them are quite visible, like these ones here, but a lot of them are just these tiny specks, and these are not stars. These are fully fledged galaxies. So it's quite an image. So you might have seen images such as these high resolution color images of galaxies. They're great to look at, and they're great sort of terms of generating interest in astronomy and publicity and all of that. However, obtaining these images requires significant telescope time and processing power, and sky surveys, which are the systematic efforts to map lots of areas of the night sky. They prioritize breadth over depths. So they'd rather hit larger areas of the sky rather than studying a few objects intensely. So rather than looking like this, the galaxies that astronomers end up working with look like this. I'm not sure. Yeah, all right, okay. Yeah, there was this, yeah, anyways. Yeah, so it just looks like that. And there's a fair bit that you can get from these images, such as, the intensity and the shape and overall, but you wouldn't send that out into the public to advocate for astronomy or anything. So how are galaxies studied? Well, so there is a need in studying galaxies for multi-wavelength astronomy, or a multi-wavelength approach. And that means that different telescopes may study the same object you are using different wavelengths, different segments of light. And the reason is as such. We'll get it now into the electromagnetic spectrum. So, fresher on the electromagnetic spectrum, we have on the left, I'm hoping it's the left, yeah, I'm guessing stage left for you as well. The left-hand side, the least energetic radio waves going up in frequency or down in wavelength. We progress to higher energy waves up to X-ray and gamma waves. So the portion we are most interested in is this range here from the infrared to the ultraviolet, including also visible, because that is the range in which stellar activity, that is the activity of stars, can be detected. So we'll focus on this range. And something to bear in mind is that all bodies, basically, it's a fundamental law of physics that any body emits electromagnetic radiation that is proportionate to the temperature of said body. So basically, the hotter something is, the higher energy, lower wavelength the electromagnetic radiation it emits is. So for everyday objects, around us. So for example, we emit in the infrared range, people, that is, animals, mammals, whatever. A bonfire may emit in the visible, and these arc welders here, which are they get quite hotter than regular fire, if you will, they emit a fair bit in ultraviolet. So again, the hotter, the bluer, if you will, the light, up to ultraviolet, where we don't see it, essentially. So what about stars in this spectrum of temperature and radiation, if you will? Well, on the lower end of the spectrum in terms of temperature and higher end in terms of wavelength, we have red dwarfs. Now, they are the most abundant type of star in the universe. They have the longest life of any star because they're very cool and energy efficient, and they have surface temperatures ranging from 3,000 to 4,000, so they emit mostly in the infrared. On the other end of the spectrum, we have these O-type stars, which are they are much more massive. They're very rare, constituting that number as a percentage of all of the stars that we have studied or observed, and they have surface temperatures of up to 50,000 Kelvin. Now, our sun in the middle here has a surface temperature of around, let's say, 5,700 or 6,000 Kelvin, whatever you want to call it, and it emits mostly in the visible. So, in terms of galaxy morphologies, and morphology just means shape or form, there are two main types. There's several subtypes and mergers and irregulars and whatnot, but the two main subtypes of galaxy morphology are the spiral galaxies on the left. So you see here they have, well, spiral structure, and these elliptical galaxies, which are mostly round, mostly oval shaped or circular or whatever, but there's no structure whatsoever. And so for these elliptical galaxies on the right, they contain mostly older stars. That means there's little to no UV emission. It's again, most of the stars are these older, cooler stars, and so infrared is sufficient to study these populations of galaxies. The same can be said of the center of the spiral galaxies. Again, mostly older stars, little to no star-forming activity or little to no UV emission, and so infrared is sufficient. Again, however, these spiral arms are sites of ongoing star formation, so they contain young, very hot in terms of surface temperature, blue stars, and so UV is a prerequisite to studying these areas. And studying these areas is very important because understanding the rate of star formation in a galaxy is important to understanding the galaxy itself. And you can actually see in this image here of a spiral galaxy. So the center here is more orangish, reddish light, and the spiral arms are bluer. And that again is an indication of different types of stellar populations. Right. So, in terms of these different types of galaxies under different wavelength observations, so for each row, if you will, of images here, we have a progression from infrared to ultraviolet, with the top row being for a spiral galaxy, the bottom row being for a elliptical galaxy. So again, you see in the top row, the spiral arms are more highlighted in the ultraviolet area, whereas when we go back to infrared, it's the central area that is more highlighted because it's the one that emits mostly in the infrared, containing, again, older, cooler stars. The elliptical galaxy, I mean, there's no structure to speak of, almost no structure to speak of, and most of the, like the highest signature in terms of the light is in the infrared/visible. So, moving on. So these sorts of black and white images are quite boring, and to be quite frank, I spend a lot of time just studying these images and looking at them and seeing the outputs of models and whatnot. So what I did was I just added some color so that it's not as boring to look at. But again, these are sort of black and white images, but with a filter on top, and this color scheme will carry forward. All right, so my goal is, or the goal of my thesis was to use generative AI to basically learn a mapping, if you will, between observations of the same galaxy taken in different sections of the electromagnetic spectrum. So we would have, for example, an image, say, of a galaxy in infrared. We would plug that into a generative AI model, and hopefully, if all goes well, we would get a image of the same galaxy, but under the ultraviolet, or what it would look like if we imaged it in ultraviolet. So you can think of it as a prediction in ultraviolet, and vice versa. We can train the model in the opposite direction. This is why there's arrows going in one direction and the other, because it really doesn't matter which direction we go. It just depends on the specific applications. Now, the motivation for this, and to give To explain the motivation, I will take this Hubble Ultra Deep Field image as an example patch of sky. So let's say you have this patch of sky and you want to study all of it in ultraviolet. But let's say that you have an ultraviolet telescope that, due to limited resources, is only able to study I really hope it's the same for you guys, but the right patch of sky. So it's only able to study this right-hand side of a patch of sky. So you don't have ultraviolet observations for the left-hand side, right? Which is, bummer, but resources are resources, and that's what you can do. However, if you happen to have infrared observations for the left-hand side of the sky, given if we have a decent generative AI model that can perform these transformations, we can plug our infrared observations into our generative AI model, right? Get ultraviolet predictions, and now we have the whole patch of sky mapped in ultraviolet, if you will, without having to put in double the resources that you would under our normal conditions. Now, again, one half would be observed, the other half would be predicted, but having a prediction is better than nothing at all, I suppose. So now that we've motivated all of this, what is this generative AI that we'll use to perform these transformations? Well, generative AI, like it's all the rage nowadays because, like, I mean, ChatGPT is an example of generative AI. It's an example of text-based generation. An example of image-based generation is this project called This Person Does Not Exist. And this is an actual website. So if you go on your phone or on your laptop, you put in thispersondoesnotexist.com, you will get a website that generates faces of people that do not exist. And I'll give like a quick pause here. Can anyone, and maybe you don't have to answer this, but can anyone tell which of these people are real and which are fake? God, I wish I was in person so I could see any. But trick question, they are all fake. So it's quite creepy actually. But again, these are not doctored images, if you will. So an image that of a person that maybe they changed their eye color, hair color. No, this is completely generated from scratch. Again, literally this person does not exist, or these people do not exist. Moving on, our specific application of generative AI are these image-to-image models. So they, rather than generating images from nothing or generating images from noise, they generate images that are conditioned on an input image. So it's this transformation from one domain to another. And examples of this are going, say, from photo to painting of the same photo, painting by Monet perhaps, or an image of a horse to an image of a zebra, or say a landscape in winter and transforming it to what that landscape would look like in summer, which is exactly what we would want. Say instead of winter summer, we would have infrared ultraviolet or something like that. So again, our purpose, from one band to another, and we're going to use our image to image models. Now, in terms of training these models or getting these models to perform how we would want them to do, what we do is we basically take thousands of labeled examples. That is an input example that has a corresponding target, and we pass these examples to the model and give it the opportunity, if you will, to learn the necessary transformation. This is done by essentially minimizing the distance between this output, which at first is noise. So minimizing distance between this output and the target until the images line up almost perfectly, or as perfectly as we can get them. Right. So in terms of training data, what we need for this approach is paired data to learn the transformation from one wavelength to another. So what that means is for each galaxy, we would have input, but also a corresponding output label. And you can see here that they are indeed paired because, line is just the galaxy is the same. It's just the structure and diffuseness, if you will, is different. So we need paired data to learn a transformation. So from where will we get our training data? Well, the good news is astronomical surveys, almost en masse, have made their data available to the public. However, there's a few challenges with getting data from these surveys. So on the left-hand side, we have this option of going with real data, and the difficulties with this is that one, navigating these databases is non-trivial. I personally spent a number of weeks just trying to get some image, and it was quite frustrating to see how immensely convoluted and vast these databases are. So that's one challenge. The other one is that we have to account and correct for instrumental differences, that is varying degrees of background and noise levels. So you see here, these are real images, and one, there's a lot of noise, and two, there might be some artifacts in the back, some stuff that isn't part of the galaxy, like stars or other galaxies, which may make the task of learning these transformations difficult. However, simulated data, it's ideal, which could be a good or a bad thing. The good thing is that there's no noise, there's no artifacts whatsoever. The bad thing is that that's not realistic. So when we go to real data, it's sort of on some, I wouldn't say a toy model, but it is ideal, right? Which makes it easier on the model to learn. It's also a lot more easily accessible, and we have a wide assortment of bands or of wavelengths. So the simulated data that we decided to go with comes from the Illustris simulations. So the Illustris simulations are a cosmological simulation. They evolve a simulated version of the universe over around 13 billion years, or over its 13 billion year lifespan, which is roughly how old our universe is. And this image on the right-hand side is just a mock-up of what the universe looks like from the sort of largest scale. And so if we were to zoom in here quite a bit, we would eventually get to galaxies. So if you imagine this is, if you will, a sandstorm, the galaxies would be the individual sand grains in said sandstorm. So what makes Illustris special is it can make predictions about the internal structure of galaxies. So that is, again, a model, imagine, if you will, that cannot just model a sandstorm, but the individual sand grains, right? And that's because it includes comprehensive physics and feedback mechanisms, as well as other fancy stuff that I'm not qualified to talk about. So these images that we've seen before actually come from the Illustris simulations. This is just a few examples. We'll give others, obviously. There's that. So moving on, how realistic is Illustris? Because if it's not realistic, then our model there may be a discrepancy between or it may not be a good indication if our model performs well in Illustris, whether or not it will perform well on real data if Illustris itself is not realistic. So to answer this, I will go back to this Hubble Ultra Deep Field, and well, the thing about this image is half of it is the Hubble Ultra Deep Field, and the other half split down the middle, down the center, vertically. The other half is generated from Illustris. So one half from Hubble, real observed data, and the other is from Illustris. So yeah, pretty realistic to me, just in terms of visually assessing things. So photometric bands, because previously we had talked about the electromagnetic spectrum as just this spectrum going from infrared to ultraviolet or whatnot, but astronomers use these sets or the set of well-defined filters with a specific sensitivity to a given wavelength. So we don't just talk about ultraviolet or visible, we talk about a specific section of the infrared or the ultraviolet, and we give it a name. Sometimes the name stands for something, sometimes it doesn't. So for example, this band here, we call that the FUV, or far ultraviolet. It has a wavelength of around 150 nanometers. then to U, 360 nanometer U for ultraviolet, B, G, and R, that's your visible bands, and BG and R, that's blue, green, and red, because these actually correspond to, well, blue, green, and red light. And then your infrared bands, you have Z, K, and then a smattering of others that are somewhat irrelevant. But you don't have to memorize any of this. I will circle back to this chart as we progress and as we need it. Right. So I conducted two main types of band predictions. So the first is interpolation. And interpolation is essentially, if I give you a sequence such as 1 something 3, and I ask you to infer the number in between, that would be interpolation. So interpolation is simply we have a sequence and we try to infer something within this sequence. And integers only, 1 something 3, what would come in between? 2. Great. Extrapolation, on the other hand, is extending a sequence. So it's going past the endpoint. So rather than circling back and going in between, we're going on the outside of the endpoints of a sequence. So 1, 2, next integer, well, it could be 3, but it could also be 4. We could be doubling. We don't know the pattern. And this is just a very simple or simplistic explanation as to the difference between interpolation and extrapolation. But the one thing to bear in mind is extrapolation is inherently more challenging because we are going outside the bounds of a given sequence. So for our bands, an example would be, so for interpolation, say we could have the U band from the ultraviolet and the K band from the infrared, and we would try to infer the G or green band in the center. So again, we have on the outside these two bands, and then we go in the center. Extrapolation would be, say we have B and R as our input bands, so that is blue and red, and we would go outside to the near ultraviolet, right? So it's going outside of the sequence. So first up, the interpolation results. What we did is we took 4 different models. So each model is has the same inputs. So the inputs are the U band in the ultraviolet and the K band in the infrared. And despite the inputs being the same, so just to clarify, like 4 different instances of the same model. So it's not the same model, but it is the same, or it's not the same instance of the model. It's a different model, but the same architecture, the same structure of the model, if you will. Anyways, so each model maps to a different output given the same input. So we have Z, infrared, R in the visible, G in the visible as well, and then B, blue, in the visible. And, and yeah, so 4 models, but however, G and B are very similar, 450 and 470. So no, thank you, G. Like there's no need basically to include the results of G. So these are our input pairs. These are, again, paired images for the input. So the top row are your U or ultraviolet observations. The bottom row are the K or infrared observations. And you see here there's a fair bit of difference in the inputs. The difference obviously comes from the fact that in the UV we have these star-forming regions that are front and center, and in the infrared it's the older stellar population, and so you have way more diffuseness as opposed to way more structure in the UV. Right, so we'll look at some target versus generated image. Target is what we want our model to, well, model or replicate, and the generated images are the output of the model. So for the Z band predictions, on top we have the target, and on the bottom we have the generated images. There's a fair bit of agreement, both in terms of diffuseness and the structure. I mean, at least to the naked eye, virtually indistinguishable. For the R, and I'll go back and forth just one more time, and perhaps keep your eyes here and take a look at what happens to this region. For the R, you see here the star-forming regions are a lot more prominent compared to the Z. And again, there's a fair bit of agreement. And then finally, for the B, now the star-forming regions are way more prominent, and the structure is much more or much less diffuse, if you will. And again, fair bit of agreement. Now, to look at a progression, just to see how our model is able to capture the different qualities or characteristics of each band. We have the input K or infrared on the left-hand side. On the right-hand side is the ultraviolet, and then our three generated bands fill in or are delineated by our inputs. So again, there's a clear progression from star-forming regions to more diffuse areas. And similarly with this bunch, like one really good example is this line, if you will, here of star-forming regions. It gets further and further obstructed or further and further attenuated as we progress to the other input. Now, extrapolation results. Now, the extrapolation is again more challenging, but further on top of that initial challenge of simply having to extend the sequence, we decided to test our model with lower wavelength transformations. So that is taking from the sampling from the visible, so B and R, and then going to U and then UV. So the lower wavelength transformations are more challenging because there's more structure to infer. Right, so we took two models, same inputs, B and R, and one mapping to U, one mapping to NUV, which stands for near ultraviolet, by the way. So these are our extrapolation input pairs. On top we have R, on the bottom we have B. There's not a huge difference because they're much closer to each other than with the input pairs of the interpolation. However, there's enough difference in diffuseness and in structure to allow the model a chance to learn the progression. So in terms of target versus generated, on the top row here we have the input or one of the inputs B, but it's the input that's closest. And on the bottom we have the target. I will only show the NUV for brevity's sake. So these are the just check. Yeah, so bottom we have the target NUV, and then the middle row is the generated NUV. And despite the complexity in the structure and there not being any diffuseness that our models can perhaps hide behind, the output matches nearly it's not star really, but it's region for region, if you will. Like you can trace every single region in the target and find it in the generated. The signatures are quite, they match up fairly well, right? So that is extrapolation. Now, oh, thank you. Okay, so this has been so far a qualitative assessment of our model's performance. So we've just been looking at images, but in terms of quantitative measures, we want to be able to quantitatively or numerically assess the quality of the outputs. And I won't bore you too much with the numbers, but one quantitative measure is the SSIM, or Structural Similarity Index. What it does is it's basically a function that takes in two images and it outputs a number, and that number indicates basically how close these two images are together. So an SSIM score of 1 indicates perfect agreement, and 0 is no agreement whatsoever. So it goes from 0 to 1, and 1 is, well, 1 is ideal because it means that the target, right, and the output or the generated images are perfect, which is what we want. So a few examples. So these are two completely different galaxies. They have an SSIM of 0.28 because, again, there's very little in common between these two galaxies. Now we're looking at the same two images of the same galaxy. However, the bands are far apart, are in the visible, NUV in the ultraviolet, and so the SSIM climbs from 0.28 to 0.49, and if we make the bands closer, the SSIM will climb up from 0.49 to 0.78. So this is just an indication of what the SSIM score stands for. Now, for our extrapolation models, again, the mean is, the 1 is ideal, and the statistics were calculated on around 500 images, but the mean SSIM we got for the near ultraviolet prediction was 0.96, and for the ultraviolet was 0.99. So these are very, very good scores. This indicates that the images, the target images, or sorry, the generated images are indistinguishable from the target images. Now, there is one other quantity, if you will, that we can use to assess the quality of not quantity to quality. That sounds bad. But anyways, we can use it to assess the outputs of our model, and it's the Gini coefficient. Now, the Gini coefficient traditionally is used for economics, right? But an astronomer figured out, I believe in 2004, that you can use it for galaxy morphology classification as well. So instead of calculating wealth distribution, the Gini coefficient now calculates distribution of light within an image. So ranges from 0 to 1, values close to 0 indicating perfect equality, and values closer to 1 indicating maximum inequality. What does that mean? What it means the following. This is just an example of different light profiles. So the farthest on the left here, the light is fairly evenly distributed, and so it has a low Gini coefficient score. And as the light gets more concentrated or we get to a more unequal distribution of light, the Gini coefficient climbs to 0.95. So it's since its introduction to astronomy, it's been used to classify galaxy morphology, and it's a great way of assessing from a galaxy morphology perspective if our generated and target images are similar. So for the Gini coefficient, there is a mean difference for the NUV band of around 0.76%, and for the U band of 0.53%. So again, these are this is thumbs up, good, nearly identical, and certainly quite promising. Now, finally, this has so far all been about illustrious. What about observed data? So this is really the true test of our model's capability. The whole point of developing these models is to augment existing observations. There's really no need to augment illustrious because one, it's synthetic, and two, it's already there in all observable bands. So what we really want to do is run these types of models on real data in the real world. So we trained one model using real data. It's a single interpolation task with the inputs being G for green and Z for infrared, and trying to infer the R band in the visible. G is visible as well. This data, by the way, is from SDSS, if you know what that is. And so these are our inputs. Top row is the G input, bottom row is the Z input. You can see again, there's more structure in the lower wavelength and more diffuseness and more, well, just blobs of light, if you will, in the Z input. So finally, the target R is on top and the generated R is on the bottom. And we see, again, a fair bit of agreement between the signatures of the structure and as well the signatures of the bulge or blobs of light or centers or whatever you want to call them between the target R and the generated R images. Finally, for the observed interpolation, again, the SSIM, the ideal is one. We have an SSIM score between the generated and target images of 0.86, which is not nearly as high as the 0.99 and 0.96 that we got before. But again, these are real images, and so there's a lot more noise, which contributes to that sort of disparity, and the mean difference in the Gini coefficients between target and generated is 2.5%, which is not perfect, but it's still pretty decent. So takeaways is the results are not perfect for the real images, but they are very promising. And we have learned that image-to-image models, they can be used to augment existing survey data, and hopefully this will be a very promising area of further research. Future work, we'd like to train using more observed data, so perhaps different surveys or even going outside of one survey to another, so we can have a wider range of bands. And we also like to experiment with more band combinations. So maybe going in the opposite direction instead of going, say we used U and R to go to, or B and R to go to NUV, would like to go in the opposite direction. Anyways, thank you. And any questions, please?
I'm gonna unmute so we can clap.
Oh, thank you.
So thanks very much for a really interesting and talk, Youseef, and something we haven't heard about before. And I'll ask people in the room about questions. And Randy, were there any on the chat line? So I guess I'm talking. So you're still there, right?
Yes, I'm with you. I'm with you.
Okay, yeah, it'll switch between us. Actually, what I can do is I can figure out how to do this.
Would you like me to stop sharing?
No, just leave that up for now. I'm just
Okay.
trying to, I wanted to. I was just wondering if you could say a little bit more about how this might be used going forward. Now, presumably it will need some more testing. At what point do we go from the sort of testing that you're doing to someone actually using it, not just to sort of test with real data, but to actually try and get some information from it?
Yeah. So let me go back. Perhaps this slide might be useful. Yeah, so in terms of running this in the real world, there's a number of obstacles or of things that remain to be done. So the first is like we need to do more testing on real data. So that involves collecting, potentially cleaning, because cleaning data from different sort of surveys or different sources is quite an intense process, especially from different surveys, because there's different uh, instrumental differences and different noise signatures, and as well different even resolutions of the images have to be lined up, and sometimes even the same coordinates can point in different directions. So there's a fair bit of work that has to be done in terms of validating whether the transformations that we've done on simulated data are possible with real data. But I think that it is possible to advance, simply because, so one thing that has been done in the past is, it's been done a few years ago, is there's these researchers that managed to simply map the noise signatures. So what they're doing is looking at just random patches of sky, right? And they used AI to map the noise signature from one to the other, meaning they can transform from one survey to the other. Simply, again, all else being equal, they just managed to transform in terms of noise signature. So given that something like that is possible, if we add that on top of our capability to transform just within one survey, it certainly should be possible.
So I guess I'll keep asking until there's another question. So the fact that you can do this, sort of go from, and let's say the extrapolation, that you can look at some images in the visible and get a more or less one-to-one correspondence with what's going on in the UV. I guess one of the things that says right away is that that there is a one-to-one correspondence, that the information that's contained in the UV is still somehow present in those other wavelengths. So if you have a little bit of information, it's not that there can be a big variation in a different wavelength. I mean, is that one of the conclusions from this?
So yes and no. So in a sense, in a sort of ideal sense, yes. you can sort of amplify certain signatures and having sort of a remnant of star forming activity available in the, say, G band can be amplified into the U band. However, in practice, it may be really tricky because there's all sorts of, and I talked to Professor Hilding about this, and he said that there's all sorts of odd structures and odd activities that may be anomalous, if you will, in terms of not having this one-to-one transformation. So what we mostly did with Illustris is proving that in ideal conditions, the physics can be learned, the physics can be transferred, but in the real world, we may have to experiment with other types of populations, perhaps galaxies that have different sort of signatures or different anomalies before making sure that it's a-okay to go. But what we can do for now is, I mean, say you have 10,000 galaxies that you want ultraviolet predictions for. If the model is able to give you predictions, decent predictions on 5,000 of them, 5,000 of the most regular, well-behaved ones, that's a start, I suppose, and that can be used to at least prioritize certain areas of sky for real observation.
Okay. Any questions from the audience? I do have one more. I have one sort of provocative question. And this is more from the point of view of being amateur astronomers, like most of us are. And we take pictures of galaxies, pictures of objects, and some people spend a lot of money on cameras that have a very, a full response across the spectrum, and they pay a lot of attention to, the response function of their cameras. And some of us are cheap and just get a DSLR that's got a fairly limited response. But if someone and amateur astronomers will spend a certain amount of money on software to enhance their images, and I'm just wondering if at some point someone's going to come out with a program that uses AI to fill in the hydrogen alpha that I can't see with my unmodified DSLR. Now that would be cheating. I can see I've stirred up Chris now.
This is used for fulfilling in blanks. If you're assuming that all stars are black bodies, that's a regular behavior, et cetera, et cetera. But if you're talking about anomalous emission line objects, like Gillian was saying, et cetera, you totally rule out possibility for discovery of anything with this. This is a useful tool for smoothing the picture and filling in holes if you're looking at consistency of a survey across large stretches. But you're making it up essentially in a fancy way. You're cutting yourself out from discovering anything new.
Okay.
You're just interpolating for what you've already
Okay,
got.
so you can use it for sort of statistical.
Well, it's a prediction in the sense of, like, if you go on the weather app today and you look at tomorrow's weather and it says, well, it's -10 or let's say it's raining, right? And it's going to be raining quite a bit at 5 p.m. Like, if you're going out at 4:30 and it's, it starts raining at 4:30 instead of 5, well, then the prediction was useless. Well, no, not really. It wasn't perfect, but it told you sort of ballpark it's going to rain around 5. So in the same way, our model is a prediction, and this prediction is predicated upon the training data. So it's only as accurate, only as realistic as the training data can be. So if the training data is somehow incomplete or irrepresentative of the actual population of galaxies that we want to study, then it's not going to perform well. So it's, it relies on the data, but it is a prediction, and it's not made to replace observations. It's made to perhaps augment observations. So again, if we have an area that's unexplored, what we could do is generate prediction, and based on how interesting these predictions are, we could then allocate resources perhaps more efficiently to study areas of interest.
Okay, yeah, I was being provocative and I did.
No, please. It is a
Okay,
provocative topic.
so let's thank Youseef again, and thank you for staying up so late. And
Thank you. Can I say a quick word?
And you're welcome to stay in. We're going to go through some of our observations.
Yeah, could I say a quick word, Professor?
Sure, yeah, go ahead.
Yeah, so like just a quick thing, I am currently looking for a job anywhere in Canada, really. So if anyone knows of any data science or machine learning opportunities and is feeling charitable, feel free to ask for my email from Professor Morrow and reach out to me. I would really appreciate it. Thank you. That is all. And thank you for listening.
Good, and good luck with that.
Thank you. Thank you.
Oh, Randy?
I'll try to have the YouTube of this session up as quick as possible.
Yeah, so Youseef,
Yes?
we're going to we record the meeting.
Yes.
And so what Randy's saying is that he's going to process this and put it up on our RASC YouTube, RAC St. John's RAC YouTube channel as quickly as possible. So if you
Okay.
want to refer people, if you
Oh,
want
that would be lovely. Yes, yes, yes.
to see
I
your
understand.
talk,
Yeah.
it will be available pretty quickly. So we can actually let you know when it's posted.
Please and thank you.
Give you the link to that.
All right. Thank you so much.
Okay, so I'm going
Right.
to do some observations now. I know it's very late.
Yes. All right. So good night for now.
There were thanks in the chat as well, right?
Oh, yes, and Youseef there, Jim, Stacy, Marcellus, people said, thank you very much. Great talk. Very
Yes.
well, good explanation.
Yes.
You can see all of that as well.
Awesome.
Okay.
All right. All right. Farewell.
Okay, so I'm going to share my screen now again. Let's see how, oh, I know, all I gotta do is I need to move that over there and share screen 2. And Randy, is that good? You
Should
can,
have asked if we had a spare room for the eclipses coming up.
oh, so, okay. So Randy, does this look okay to you? It's because this is screen 2. I'm not sure why it's showing that now. But you can see this on Zoom now.
I'm seeing my own picture.
Oh, I haven't clicked share yet. There was a reason the 2 was there. It's because I'm an idiot. Or tired. Okay, so as some of you may have noticed, it wasn't the greatest month for observations, but there were some, amazingly. So Randy, I don't know what the sun was like the rest of the time, but January 4th, well, we didn't see the sun. So one of the days we did see the sun, that's quite an amazing set of sunspots. So I'm glad
Middle picture was taken 30 seconds before the other 2.
Oh, yeah, so what Randy's saying, the middle picture is 30 seconds before the other 2, and you can see the clouds.
AI generated.
Yeah, and so there lots of activity. So that's the great thing about the sea stars, is that even when the weather's, and we're going to see an example of that, most of the observations we're going to see today are sea star, because you can do it in a hurry. Okay, and so David, who's online, so some of these are older pictures. David actually shared a lot of his pictures from 2024, so some of them are reminders. So nice picture with his sea star of Comet 2023 A3 Susin Atlas. And so that's a no, there's another one that I'll mention that one at the end. You have 10 minutes to see it tomorrow and then you're done. And another one from David of the Moon in October. And if you remember one of our previous meetings, I think was it David had a picture of the plane going? David, are you there? Oh, okay.
It was his.
Yeah. And John Nugent, this is now, so this is into December. And Randy, the moon with some earth shine in January. So we got a lot of pictures from January 3rd.
Beautiful Friday.
It wasn't.
And one of the things that was happening January 3rd was that Venus was close to the moon. So lots of people, John Petals, or Andrea's picture, Nikolai,
Nice.
lovely picture, always a lovely picture from Jim. And you can see the earth shine there. A bit more red on that than I have on the screen, but and Sue, there's Venus. So everybody had the same idea, and Chris has another lovely picture with the earth shine there. And so
Background stars were in Jim's too.
Two of them.
Oh, yeah. I'm impressed that
Yeah.
he got the bright part of the moon exposed with the dark part.
Yeah.
Lovely.
Yep. He's very good at that. Good work, Jim. Is Jim still there? Yep. And I had to try January 7th, which was about a week ago. That was the night that Chris said there was going to be a shadow of Titan on Saturn, and I couldn't.
Yes.
I did get Saturn in my. I did get lined up on Saturn for about 30 seconds, and then it disappeared. So I did try the moon, but I still had the Barlow on, so I had to sort of patch two pieces together. And there are ways to get rid of that line, but I wasn't going to try.
Lots of detail.
And then January 13th, so that was the 7th. So January 13th, that's 2 days ago. This is when Mars was approaching the moon. So Jim got Jim, do you want to say a word about this? Jim Stacy?
Hi, can everybody hear me?
Yep, we can hear you in the room.
Okay. Yeah, this picture was roughly 10 minutes before the occultation of Mars by the moon. And those of us in town were dealing with very cloudy skies, and it began to snow just shortly after I took this particular shot. So this was as close as I could get to capturing the moon occulting Mars. And if you were to zoom in on this picture, you can actually see that Mars has color to it, and there's also a finite disk to Mars. So that means that I was able to get the focus pretty precise. And unfortunately, I just couldn't get the occultation itself.
Okay, well, you seem to be getting pretty good at this, Jim.
Thank you. I appreciate it.
Yeah,
I like
that's
the fact that Mars is exactly halfway up the lunar limb. It's like the moon is about to steamroller Mars, good and proper.
yeah,
I think it's frozen.
yeah.
Well, it depends on.
Okay, and John Peddle also got a couple pictures with a sea star. I brightened this one up a little bit. So John, do you want to just say a word about this? I brightened it a little in the PowerPoint so we could actually see it on the screen.
Yeah, like Jim was saying, it was cloudy and conditions weren't the best. I was happy that I got a picture of anything with Mars and the moon that night. I did a time lapse and it was going for about 20 minutes. I had 100 and some odd pictures to pick from, and I only saw Mars like in probably 2 or 3 different pictures, and that was one of them.
Yep. And people who are on RSCNL talk, I went out earlier in the evening and I could see very briefly, visibly, Mars and the moon, but once Mars got close to the moon, I think you
Yeah.
really needed a telescope to see it.
And then the snow started, and I didn't think it was safe to leave my sea
Yeah.
star in the snow, so I had to call it quits.
So there's one, and then there's the other one, so you can see.
Yeah, that was all I got from like 20 minutes of time lapse images.
Yeah. Well, there's a manual GIF.
Yeah.
Okay, and John did a shot, this going back to December, of Mars, and I cropped it a little bit in PowerPoint so we could see it a bit better. And I did one, so January 3rd, again, we got a few pictures done on January 3rd. And so most of the surface structure on Mars seemed to be around the backside on that day. And this was January 9th, so I got a little bit more, but this was not a good night. Trying to think what January 9th was. Was that this? No. So that was also a cloudy night. And then Chris did this one last night in the snow to get Mars at opposition, so that's pretty impressive.
Yeah, had I known you could do this when it was actually snowing, I might have stuck it out and tried the occultation. Holy crap. Greg mentioned to the list earlier that
Visibly through the cloud.
before I decided to actually put my coat on and go out, I could. The moon was like heavily filtered by cloud, and then there was Mars about a hand to the right and up a little bit. I said, oh wow, you can actually pick up Mars. Fine, that's enough. When I went out, you couldn't see Mars. You could only barely see the moon. So I was dressed and I was out, so I tried anyway. Barely got Mars in the finder and centered things, barely got Mars in the main camera. I had to shoot at 1/4 second exposures. Normally 2/50th of a second exposures to avoid saturation. That's how little light was getting through the snow. And it actually was snowing by then through the dome onto the telescope. I had to brush the telescope off when I cleaned it, when I closed up. That's only 48 images, but it was clear. It must have been some sort of a thermal inversion. You said the scene was going to be really good. It was.
Well, it was predicted that way.
Yeah.
Yep.
So what little got through was sharp, and the software could deal with it. And I was blown away when it actually pulled this image out.
Yep, lovely image.
Walk around Mars.
There's something hard between us and
Okay, and then we've got some Jupiter images. So John Nugent, again, I've cropped that a little bit so to make it a bit bigger. And David, and I looked up on December 15th, so these must be Callisto, Europa, and Io, and Ganymede would have been in there, but I think the glow from Jupiter sort of overwhelmed it. Ganymede was just sort of hitting the disk. I did this one on January 3rd, and there's Io there. And then we got a couple pictures the same night from Tim Carrick and Sue Hart using 9.25. So
Seems to be, but squashed, is that squashed?
Is the red spot on the other one?
Yeah.
they're different times.
Okay, it's a little later on.
Yeah, so this in the evening, and this is their image late at night. And you see, if you look at those two things, so this one is almost the same as mine.
It's not right focus right there. Yeah.
And David did Saturn with this game. It's going back to October because Saturn's getting pretty tough to find now. And then we have a few deep sky objects, but some of them are David's sort of yearly things. So we had the Dumbbell Nebula, so that's a planetary nebula. Down here, this is Cygnus, the Swan. And remember what a planetary nebula is a star like the sun or up to 8 times the mass of the sun. When it's stopped getting energy by fusing hydrogen in the core, it starts fusing helium, becomes a red giant, and maybe get up to carbon, nitrogen, oxygen in the core. But as it does that, it puffs up, and eventually the outer layers are so far away from the core that they can escape. And what you're left with is something like that. So there's the core is still there in the center. Can't really see there. That's becomes a white dwarf. It's not generating energy anymore. It's just hot. And the Dumbbell Nebula is an example of that. The Ring Nebula is another one, but this is a lovely shot from David with the sea star, and there you are. And M13 is a globular cluster. They're older stars that are bound together. And so here's, again, this is going to be a shot from more of the summer. But there's Cygnus. There's the summer triangle, Deneb, Vega, and Altair. And if you go in this direction from Vega, there's Hercules, looks like a keystone. There's where the Great Cluster is. And there's nothing wrong with a picture like that. So that sea star is really performing. That's from June, so that's really a summer object. And then the Whirlpool Galaxy, which is actually in terms of constellations, it's considered to be within the Canis Venatici, which has something to do with dogs. Galaxy rather than the Big Dipper, but it's seems to be closer to the Big Dipper. And it's about 23.5 million light years away. And there's, again, a sea star image of that from David. And the Pleiades, you can see that now. So there's Orion, which is sort of dominating the southern sky this time of year. And you head up in this direction, there's Aldebaran. And then there's the Pleiades. So that's an open cluster. They're younger stars. They're still hot. Remember what Youseef said, hot stars don't last very long. They're less than 100 million years old, compared to our star, which is 5 billion years old. So the young stars, they probably form together. They're probably drifting apart. And Jim has a lovely picture of the Pleiades. Only 18 minutes, but you can see this is actually dust that's being illuminated by the bright stars behind. And like the sky is blue, this scattering from dust gives you the blue light. And then IC 342 is the hidden galaxy. We've seen that one earlier in the year sometime. It's hidden really because of dust at the equator of the Milky Way. Its apparent size, it actually appears to be quite large. It's pretty close. It's 10.7 million light years away. And so there's Polaris, and there's Cassiopeia, and the Andromeda Galaxy is right there. So just to orient you, so it's over here.
That's huge.
Yep. So it doesn't look very prominent, but that's because of the dust blocking a lot of the light. This was
Did Chris got a picture of that? I think so.
Chris did a couple meetings back, right?
No, I think it was Jim,
Oh, okay, Jim, yeah.
although I'm certainly gonna give that one a try at some point.
Yeah.
It's infrared sensitive cameras.
And another galaxy here, about 30 million light years away. And again, John tried that one. And so these are now getting pretty small. They maybe need a bit more time. And then the Silver Sliver galaxy. So let's see. Here's Cassiopeia. There's the Andromeda galaxy, the Silver Sliver galaxies down in here. And that's pretty good there. And we had some discussion about that one,
Yeah,
I think, yeah.
The sea stars are better.
so the 1970s synthesizer album and
Right.
other things.
Anyways, we've had that discussion already. So the Pac-Man Nebula, so here's Cassiopeia again. It's right in here. It's about 9,600 light years away. There's some possible star formation regions in it. And again, this is from John, and you can see the sort of Pac-Man shape there. So lots of, we're lucky that people have sea stars, because we needed them this month. And the Andromeda galaxy, we know about that. It's our closest neighboring galaxy, 2.5 million light years away. It's the largest member of the local group. Our galaxy's next. And so John actually did some mosaic. I don't think John's online here. And there was one panel that went in backwards or something. So I've blocked that one out. He mentioned that in his post, that one of them hadn't added into the mosaic right. But he's learning how to use make mosaics using the sea star. And that's pretty good. And David also did the Andromeda galaxy. Oh, David's back. Hi, David. So, David, we've just been going through your year's submission and admiring the work from the Sea Star. So, good work. You want to say a few words?
Yeah, for sure. I dropped out there. Thanks, Mike. I did catch Youseef's presentation, and that was great also. So hats off to him. That was definitely interesting. I thought it was interesting how the simulation, the image from the simulation looks somewhat like nerve impulses inside of a brain. Anyway, but last year was a great year for myself, catching the comet, the Atlas comet, and so get some great use out of the Sea Star. If the weather would start cooperating now, it'd make for a great 2025. I never got to make it tonight. I'm recently moved, and I spent the evening putting together a bed frame. So
Okay, fair enough.
get the priorities.
Yep. Anyways, thanks a lot. Thanks for all the images, and you, as I said, with the kind of weather we've had, it's a good thing that there are a lot of sea stars in the group. And that's the end of the observation reports. So Robert's online. Robert, did you want me to go through this while you say a few? Oh, let's see.
Can you hear me, Mike?
Yeah, I'm gonna have to move this over. And so Randy, is that coming up online?
Yeah.
Okay.
This is our monthly sky this month, and much of it is the same month after month. So we don't need to spend a lot of time on it, just useful information for darkness when it falls, and when we can observe if there were skies to do so. The sun, as it looks today, with some sunspots around there, so there's still some decent activity if we could only see it. The looks like there's a little bit of just go back there. Yeah, there's a little bit of the text got a little bit screwed up there with the input of the image, but nonetheless, you can still read it for anyone who might be interested in borrowing our solar scope. And moving on, we have the planet roundup there, and so the table got scrambled between two pages there, but we'll get it fixed. But in any case, the green indicates visible planets that we can in our sky, should we have a clear sky. And it's not often that we get 1, 2, 3, 4, 5, but that's what we could do if we had some clear skies. Moving on, I note I had to make a note, although it was designed for the 15th, I couldn't not, as I was creating it, note the January 13th occultation, which thankfully one of our members got, not as well as he would have liked, of course, because it was only just by luck that a moment became available for him to get an image, and quite a good image too. So there's a little bit there about Saturn, talking about the rings are pretty much edge on. I don't think they're exactly edge on just right now, but it's getting very close to the sun, so it's might be the fall before we get a look at that again. January 25th, it says here the 4 bright planets in the same sky at the same time. If you look to the southwest for super bright Venus and Saturn, then southwest for Jupiter, high in the sky, and finally Mars a little bit more to the east. So maybe we'll get some clear sky and be able to take that in. And moving on, the moon is pretty much pretty fat right now, 96% illuminated. And there's some links there for some great moon tools for those who would be interested in getting a little more in depth with the moon. So by all means, do that. Comets, I couldn't find anything really viable at this time. There was Mike, you said that 10 minutes tomorrow there could be one.
Yeah, so that's 2024 G3 Atlas, and I loaded it into Chris had mentioned it, and it's very close to the sun, and so it will actually set tomorrow at about 5:15, and that's about the best we're going to get. It'll set earlier than that for the next, and then it's sort of gone.
People have been
Yeah.
taking pictures of it in the middle of the day, but you have to be fantastically careful doing that. Situate yourself somewhere where the sun is behind a building, and like going more behind the building. You don't want to accidentally have the sun come out on you when you're trying to do this stunt. I've tried to stunt once with the previous comet, and that didn't work. This one apparently is brighter, but only for a few days. This is like Mike, you said, limited time offer. Tomorrow, maybe. Is it going to be clear tomorrow?
I don't know.
Okay, moving on, some asteroids, if any, for those or anyone who wants to try and see if they can image it or see it. But you pretty much have to have a number of clear nights in a row so that you can see the motion of the asteroid as compared to the star field. So then we have our suggested objects for January. So for binocular and deep sky, and a challenge object as well. And moving further on, we see that there are four. Well, there's more than four supernova, but I mean, pretty dim when you think about those magnitudes. So, but you know, if you're looking for a challenge and we have clear sky, there some of them are possible to do. And the next meteor shower that we can look forward to would be April 21st, 22nd, the Lyrids. And I think that's probably about it, is it? No, the International Space Station passes, so you can have a look at that and see when it's available. Or yeah, as well as many other satellites as well. It's just that we only show ISS because the table would just get so large. So if you go to Heavens Above, you can pick your satellite and find out when it's in the sky.
Okay. Well, thank you. And I'd like to thank Craig too. He got that up online just before the meeting, so we're able to do that. So yeah, this is available online, and thanks to Robert and Craig for getting it for us. And so I'm going to slide that back over there and just wrap up with remind you that next month we're having a members meeting. So we really want to hear from people. Tell us about what you're doing and tell us about the wonderful things you're doing with your sea stars. Or but seriously, think about something to present on next month, and don't be shy. We're a fairly friendly audience. And remember, the Astro imaging contest and the information about that is online. Okay, so thanks everybody, and thanks to the folks at home. Thanks for joining us, and I will probably turn off the Zoom pretty soon. But good night, everybody, and
Thanks, Mike, for pulling it all together.
you're welcome. Thanks.
Thanks, everyone.
Thanks, David. And oh, of course, there's coffee, and not for people at home, but for the people here, there's coffee and treats.